we want to look at how probabilities interact with each other, or how events interact with each other. And so what we're going to do is we're going to make a rule on how probabilities are affected. And so what we'll do is we'll do two examples. We'll do rolling a die, and I'll say and tossing a coin. And so this would be event A, and this would be event B. And so I can ask the question, what is the probability of tossing a tails given that I rolled a 6, or actually for nomenclature, a 5 on a d6, right? And so this is, what is my chance of flipping a tails given that I rolled a 5 on a 6-sided die? Well, doesn't matter what I rolled on the die. Doesn't change the sample space for flipping a coin. In fact, it doesn't matter which order I do these in, right? If I roll a 5, I go flip a coin, it's still a 50-50 chance. And so that probability is 1 in 2. And we say these events are independent. All right, and we're saying the occurrence of the events do not affect the probability or the occurrence of the others. So, right, the independent events do not affect each other. And so we can say that the probability of B given A is equal to the probability of B when they are independent. Also, the probability of A given B is equal to the probability of A when they're independent, right? When the happening of one event does not change the probability, doesn't change any of the chances of the occurrence of the other event. All right, so let's look at the inverse of this. And I'll go back to the cards that we had. When I have a deck of 52 cards, drawing the first card reduces the sample space. Both in the possible, so I remove one possible outcome from the sample space. So I have less outcomes to choose from, and one particular one, there's one less of. So we call these events that where the change affects the outcome dependent events. And so dependent events, the sample space is changed by the first event. And so, again, using our deck of cards, the probability of drawing a king, given that my first card was an ace, well, normally the king would be drawn from a deck of 52, and there'd be 4 options. But because I drew an ace first, my sample space is smaller. And this is called a dependent. Now, we write our dependent events conditionally like this. There's no special formula for them. They don't condense down to simpler things. All right, so we've looked at dependent and independent events. Well, what happens? Let's look at our king example again, and a deck of cards, because there's knowledge in this. This is saying, what is my odds of drawing a king given I've already drawn an ace? What if I sit down to a table and I haven't drawn any cards yet? And so I want to know, what is the probability of drawing a king on my second go if given I've drawn an ace on my first go? All right. But let's say I don't know if I'm drawing the ace or not. So I'm sitting down and I want to know what is my chance of drawing a king on the first go and drawing an ace on the first go. I haven't done it yet. Sitting down at the table and no cards have moved. And so the probability that two events will occur in sequence, the probability that two events will occur in sequence again, we'll just use the generic A first and then B. Occur. A and B. A first, then B. And so the probability of A and B is equal to the probability of A, my chances of getting A, times my probability of B given A. And so probabilities multiply. This is very much related to our fundamental counting principle. Every time I try to do another probabilistic event and they both have to happen, the number of outcomes I'm possibly going through is being multiplied. I'm counting more outcomes. I'm getting more possible outcomes in my sample space. All right? And because probabilities are fractional numbers, these things should be getting rarer and rarer. Because when I multiply a fraction by a fraction, I get a smaller fraction. So let's do this with my kings. So the probability of drawing an ace on the first go is 4 in 52. Now the probability of drawing a king on the second draw, given I've already drawn an ace. Well, there's 4 kings left in the deck, but I'm down to 51 cards. And so when I put the probability of drawing a king and an ace, if I'm sitting down on the table and I have not flipped the 2 cards over yet, I need to multiply my 2 probabilities. And let me grab my calculator here. 4 times 4 is 16. 51 times 52 is 2,652. 16 out of 2,652. Well, let's get a decimal approximation of that. So it's about 0.006 or less than a percent, right? Because move the decimal place over, 0.6%. Which sounds about right, right? Drawing 2 cards in a particular way, that's a rare event. And this shows the rareness of the event. All right. Well, if my events are independent of each other, and I'll go with the probability of tossing a coin heads or tails, which is 50-50. And the probability of rolling a 5 on a d6, which is 1 in 6. If they're independent of each other, nothing updates the probability of, and so the probability of 2 events that are independent of each other, if they're independent, well, look what I can do here. I'm going to scroll back up a bit. If my events were independent of each other, this dependency vanishes because they're independent. I can't say B given A, and so I just focus on B. So if I come back down here to the formula I developed for events that occur in sequence, this bit here, if they are independent, so I'll do independent, I think, in purple, this probability just becomes the probability of B. This gets updated. Now your textbook writes this as 2 equations. It says, here's the probability of events happening in sequence if they are dependent. And it gives you the thing in yellow here. And then it goes, if they're independent, and it gives you a new equation. For me, I remember this equation, the P and B. And then I look at this thing here and I go, are they independent or not? So let's write down what the second equation is. And so if they are independent, not dependent. It's the probability of A times the probability of B. And so my probability of flipping a tails and then rolling a 5 on a 6-sided die is 1/2 times 1/6, or 1/12, which is approximately its decimal equivalent of 0.083. And so we have a way of finding probabilities that can happen if they change the sample space. If they don't change the sample space, then probabilities multiply. In all cases, what we're doing when we're multiplying probabilities is possible outcomes in our event. I wanted that to be an E and I wrote a 3. Possible outcomes in our event and possible outcomes in our sample space. And our sample space is always bigger than our event, right? Probabilities are always less than 1. And so when they multiply together with another one, my outcomes over top grow slow and the outcomes on the bottom grow quickly, right? I have one event, and so I'll look at the specifics here. This one event and one more event. And so using my fundamental counting principle, I'm looking at one possible outcome here, which is what I had. I had one outcome, these two things together. But the sample space that I can count from has grown larger. And so my odds get smaller. And so this number is smaller. 1/12 is much smaller than the odds of the individual event. And so when we see this "and" here, we're saying I have two separate events, but I want to see the chance of one combined event. And so we're combining the possible outcomes into one. Our odds should go down.